Hello, everybody, and welcome to the Q-MIC webinar within Future Tech Week 2020. My name is Ulrich Vogel from Carl Zeiss Company, and I will guide you through the webinar. So quickly before we really start, the ground rules for the webinar are also to be seen in the chat function. So basically, we will now, for about half an hour, present what we are doing with 3 different talks and a quick presentation of the applications we are looking into, and then we go into a question and answer session. Okay, so that's basically the agenda. 3 talks from the partners and a little more for the applications from me, and then we wrap up in time at 12. Right. So Q-MIC, we want to do microscopy at the quantum limit. So what does that mean? So we are specifically interested in very sensitive microscopy. So that means small structures with a typical height sensitivity that is better than nanometers. So that's currently basically the limit of classical interferometers that are deployed for many applications, and we want to go beyond that. So the interest for that comes clearly from applications. So we want to have improved metrology tools and inspection tools. It's also critical for improved health and biosensing, and more generally to the basic research part, we really need to know what the fundamental limits here for quantum microscopy schemes are. So how are we achieving that? So in Q-MIC, we are a diverse consortium. We have a set of different skills from the partners. In particular, that means we have a state-of-the-art so-called differential interference contrast microscope, which is pretty much on the classical limit for sensitivity in such devices. Luc Dumpelmann will talk immediately after me here about that. Then what else do we need? To get this improved sensitivity, we need a dedicated readout scheme. That is based on single photon avalanche diode arrays. Francesca will then talk about the work that is put into that. And concludingly, to really get the quantum advantage into the microscope, we also need new technology from a quantum light source to the detection via the SPATs, and then for the clever quantum readout of the information. So the basic idea behind this, quantum theory tells us that there is more information per photon to be gained if you do the detection in a quantum way, and that's what we are aiming for. Always with the thought in the back of our mind that we really need to address the applications that we have in mind here. And well, I forgot, I think, about the quantum part. That will be Alvaro's part. And to wrap up the presentation about the Q-MIC microscope, I will tell a little bit more about what the actual application needs are in our point of view. And then for the discussion, we can broaden the scope, and I hope for a lively discussion there. And with that, I directly hand over to Luc Dumpelmann from ICFO.
Great, many thanks for the introduction, Ulrich. I hope all the attendees are well. I will briefly share my screen. I hope you can see my screen now. Correct?
It's in presenter mode. You have 2 screens, I believe.
Okay, better now like this, right? Great. So as Ulrich mentioned briefly, I will present a lens-free interferometric microscope, which utilizes classical light, so an LED source, and also commercially available CMOS camera. So nothing with quantum directly, but we are part of this project to push forward the quantum version of this microscope. So before I will show you some applications and some results, I want to briefly highlight how the technology itself works. So what we currently have is a device about 10 centimeters in cube.
Luke, sorry, I think we have a small technical glitch. The slides are cut off a little bit.
On the top, or?
So they are not appearing in full. So maybe there's an easy solution.
I will. Better like this?
Yes.
Okay. Good. So this image basically shows the microscope we have now. It is about 10 centimeters each length. So it is very compact actually. And we can use it in different ways to measure the sample. So one of the ways we are using it is to measure samples in transmission mode. So with this, we basically shine a light beam through the sample. Light passes through the sample, and finally we record it on a CMOS camera as highlighted here. The technology we have basically splits the beam into two. These are polarization sensitive. The two beams pass through the sample, and then after the sample, they're interfered again, and on the camera we can measure the interference pattern. Now, if we have any geometrical features on the sample or any change in refractive index, one of the beams compared to the other will be delayed, and this delay can then be measured in the interference pattern. So with this, we have a very sensitive device to measure any geometrical features or refractive index changes. As I mentioned, there's a second mode we can use. Oh, before I go further, we not only have one beam illuminating the sample, but we're using a collimated beam. So basically we have many parallel beams at the same time passing through the sample, as shown here. So as I mentioned just before, we have a second way of measuring samples. It is in reflection mode. The technology itself works very similar. We illuminate the sample with light. It is then reflected from the sample and afterwards interfered again on the camera. The camera in this case is on the other side of the sample. So what do we achieve if we just make the measurement? This is a raw capture of first measurement, and you see there is not much information in this sample itself. What we then do is that we shift one of the beams compared to the other, and with this we have a phase shifting interferometry. With this, we can get more information about the sample. This is shown here. The sample itself is not in focus, as you see here. And the reason is that we're using a lens-free system, so we don't have a physical plane of focus. What we then can do is in the post-processing, we can kind of generate a virtual plane of focus and focus this image. This is shown here. So you now see that the features are quite well in focus. This is done with one wavelength, but since we're using collimated light, we can use any kind of wavelengths as an illumination source. And here you see the image with RGB and near-infrared light. Finally, we can also do some reconstruction of the surface with some sophisticated algorithms. And here you see the final image of 10 nanometer silica features on silica. So this is a completely transparent sample, but still we have a very good resolution of these 10 nanometer features. Also, what you see here is that we have a very large field of view. So we have about 5 by 7 millimeters in this case, but the field of view can be basically scaled much larger. So overall, these are some specifications of the microscope. I hope I was able to just briefly highlight to you. As mentioned, we can use a tunable laser source or an LED with different colors. The measurement itself takes less than a second if we just want to have the qualitative information. If we want to determine the accurate thickness of the structures, we need currently about a minute, but this is just can be further optimized with more sophisticated algorithms. And one of the highlights of this microscope is that we basically can measure in transmission and reflection at the same time. So how do we integrate this technology? Currently, we have 3 different devices which utilize this technology. One is the microscope I just highlighted to you before. This is used for an in-depth analysis of any kind of material. Then we are using the same technology as an add-on onto existing inline inspection systems, where basically you have a camera and some lenses, and we can use this technology to enhance the imaging of this device. And finally, we're also using this technology in point-of-care applications where we analyze biomarkers. I just want to give you some examples and some measurements of these 2 topics. So this is about material analysis, where we have mainly 3 different kinds of applications. One is for quality control, where you very accurately can detect any cracks or particulates on transparent or reflective substrates, as shown on the left-hand side. Secondly, we can accurately determine any changes in refractive index. And here is an example of transparent electronics. So as a sample, we used a touch display, and here you can accurately determine the edges of these transparent electrodes. And finally, what we are also investigating is to locate features on the top of the sample and inside the sample. And here on the right-hand side, you can see this is a glass substrate where we encoded some structures inside the glass and also on top. And with our algorithm, after the measurement, we can accurately determine the position of these features. As for point-of-care applications, we're using exactly the same technology and the working principle, but here we're using a cartridge which we functionalize with some receptors. We then use this cartridge to measure any kind of biomarkers which then bind to the receptors. As you see here on the right-hand side, the biomarkers will then increase the signal upon binding. And with this signal, we can correlate to the concentration of these biomarkers. To know the concentration is essential for disease diagnosis, and we are aiming here for the rapid detection of infectious disease. So with it, I hope I was able to show you some results of this classical lens-free interferometric microscope. Of this, I would like to pass on to Francesca Madonini, who will present her work on the SPAD array.
Okay, thank you, Luke. I'm going to share my screen. Okay, I hope you can see my slides. I'm going to talk about polyMe contribution in Q-MIC project, which consists in the development of a SPAD imager for coincidence detection. In fact, in a Q-MIC measurement scheme, photons passing through the sample undergoes a certain phase shift, which ends up in a certain spatial distribution of coincidences. That's why our goal was to provide a detector able to detect coincident photon pairs spread over the entire array area. We actually provided 2 different types of array, each one based on a specific coincidence detection concept. The first one consists in a 32 by 32 pixels. In each pixel, there is a SPAD, a single photon avalanche diode, which is a sensor, a light sensor which gives a digital pulse every time a photon impinges on it, plus in each pixel a time to digital converter, which is able to register the triggering instant of the SPAD. It means that whenever a photon impinges on the array, its TDC, its time to digital converter, registers the triggering instant. And also when a pair impinges on the array. The TDC has a resolution of 312 picoseconds. Then the chip undergoes a full matrix readout reading all TDC's content, even the one of the empty pixels. And then in post-processing, coincidences can be detected just looking for triggering instance within a certain coincidence time window. When we increase the number of pixels to improve the field of view and improve the resolution, this approach brings to a long readout time and high data throughput, but low useful data, because we are reading also the empty pixels, and high power consumption. That's why, with the aim of increasing the number of pixels, reaching almost 100 by 100 SPAD pixels, we developed a completely new array with a different detection concept, which is a non-chip detection and mapping of photon coincidences. In order to clarify this concept, we can see that if a photon impinges, a single photon, now nothing happens. If another single impinges, nothing happens. But when a pair arrived within a coincidence time window of almost 2 nanoseconds, an event-driven logic is activated, transferring outside a strobe signal indicating the presence of a coincidence and the X and Y position of the pairs, of the coincident pairs. And again, if a single impinges, nothing happens. And if another couples arrive, again, the event-driven logic is activated, giving the strobe signal and the coordinate of the position of the pair. This approach guarantees a faster readout of only useful data, and now no external processing is needed for coincidence detection. Everything happens directly on chip. This new SPAD array is developed in BCD technology, which is a smart power technology which ensures high performance integrated SPADs with a high detection efficiency reaching 60% at 532 nanometers. Low noise, and to understand how low, for example, 100 counts per second for a 10 micrometer diameter SPAD at 50 degrees, and the best in class timing jitter. This is the array we actually designed with the aim of reaching almost 100 by 100. The array we actually designed consists in 96 by 96 SPADs with 10 micrometer diameter SPADs and 50 micrometer pitch, which brings to a native fill factor of 3.14%. This array is based on the on-chip coincidence concept, coincidence detection concept, with a coincidence window of 2 nanoseconds. It is also based on the event-driven readout that I was explaining before, and we are able to transfer outside 48 addresses of coincidences in a very low time of 330 nanoseconds. As a fill factor recovery strategy, the array will be coupled with a microlens array in order to boost the collection efficiency of 25 times. The microlens array will be developed by MPD, Microphoton Devices, a spin-off of Politecnico di Milano. MPD microlens array ensure very good uniformity on the chip area and good X and Y alignment. It is coupled with an anti-reflexive coating between 350 and 900 nanometers. And here we can see an example of image acquisition taken by an MPD commercial camera, alone on top and coupled with microlenses on the bottom. You can directly see an improvement of signal of 25 times And in this way, also hot pixels, which are pixels with a high dark count rate, are now completely overwhelmed by this increase of signal. And with this, I thank you for the attention, and I leave the floor to Alvaro Cuevas.
Thank you very much, Francesca. Thank you to the other speakers and the organizers. You did very well. Well, in this section, I would like to talk about peak flow contribution, which we integrate quantum light and quantum detectors to fully reach the unconventional supersensitivity expected by the project. The aim of this project, as pointed out before, is to develop a quantum microscope for imaging and metrology in a portable device and having a non-classical. How do we do this? Basically, by taking advantage of integrated quantum light, the LIM configuration developed at IFCO, and single photon image devices as the one developed by Pauling and MPD. Before, I would like to talk about a few differences about classical and quantum light, because it's essential to understand why quantum can beat classical under certain scenarios. Essentially, classical, well, any kind of light is composed by single light photons, but in the case of classical light, the photons are randomly placed in space while they propagate in one particular direction. In the case of quantum light, you can have some weird effects, for example, connection between photons in time and space. These are called usually as correlation of entanglement or entanglement. So if we go back to the classical LIM device, one can think that every beam that contains single photons, for each one of them, the orthogonal projection of each photon is split into two arms. So then you obtain interference, which is registered at the end with normal standard cameras. At the end, what you simply do is to expose this camera to more and more light, and then you obtain interference images. In the case of quantum light, instead, when two or more photons are passing through the sample, you need to register multiple coincident events. In order to do that, you cannot continue with the standard imaging devices, but you need an unconventional bad array. So the classical method is very useful, but intrinsically limited by the number of photons, while in quantum light, you can reach other limits. This is one example of how phase sensitivity in the LIM could be improved from the classical to the quantum case. In the classical case, if you scan a relative phase between the two arms of the interferometer, you can see that there is an interference fringe here on the left. These are, well, let's say, single photon interference images. And the associated error or noise in the phase scales as this equation here below. This is usually called as shot noise limit. In the case of quantum light, when you have multiple photons, if the number of entangled photons described here by M increases, then you can, for instance, decrease the effective noise. So in the limit, when all the photons are entangled, you can reach the Heisenberg. And here on top, you can see that actually with two photon states, you can increase the effective phase resolution. So we don't see a single cycle, but we see two. First of all, how can we produce this kind of light? Normally, this kind of light, article, is produced by nonlinear effects, which are, for instance, the parametric down conversion, in which a highly intense beam, like a laser, is pumping a nonlinear crystal, which generates two photons for each photon that was absorbed. This phenomena occurs basically conserving energy and conserving momentum. So if one photon is generated to the left side of the far field, another photon will be, its coupled photon will be completely at you can see here below, where the centroid of mass of the two photons are always at the center of the channel. By the way, this image was taken with one of the SPAD arrays. So the novel target specifications that we are planning to reach are to increase the phase sensitivity far beyond the classical one. So it's not just below 1 nanometer, but we expect angstrom. We expect also true quantum noise reduction, as explained before. These pads will have an internal built-in multi-photon readout, and together with the collaboration of Fraunhofer Institute, we expect to have a very low wavelength source, which will allow us to increase the effective resolution, phase resolution. I mean, a few benefits about the technology, for instance, high compatibility with the standard applications already developed for LIM. As explained before, using low wavelength, low effective wavelength, you can reach UV resolution. For instance, by using single two photon states, you don't damage delicate samples like bio or synthetic compounds. And finally, it opens new ways for new ways of analysis, phase sensing, as developed by another of our collaborators in University of Glasgow. Here, I show you one demo prototype on the left, containing all the main optical components and the SPAD array on top. On the right, you can see complementary images of the sensor in two hemispheres of the sensor, showing a phase shifting digital holography, which is basically a phenomenon that occurs when you scan the phase between the two arms of the interferometer. This was taken actually with a single photon source, and reaching this amazing kind of behavior. Two challenges that we expect and we have seen that strong optical losses can increase the acquisition time. Spurious detection requires sophisticated filtering based on spatial correlation, for instance, and huge amounts of data could require unconventional strategies for taking information from it. Thank you. I will pass the word to my colleague here, Ulrich.
Thank you, Alvaro. I think at least on my side, the connection was a little shaky, so that was not as good as when we did the test run. So maybe everybody else could hear it a little more clearly. Happens when you go live. If there are more questions, we still have time for that afterwards. Right. So I go on with what we think are really applicable use cases for the Q-MIC microscope. So, well, it's three as Luke already showed in his presentation, and they are true and interesting for both the classical interferometer and for the quantum upgrade we are intending. So the first one is metrology and inspection for transparent samples. So here the benchmark is that you want to have a very high sensitivity towards the refractive index. So in absolute numbers, relative refractive index in absolute numbers, 10 to the minus 5 or 10 to the minus 6. And so that is possible with very dedicated metrology systems right now, but that's not very reliable. The calibration of such devices is very tricky. And it's definitely right now not suited for high throughput. So that's what we are aiming for here with the Q-MIC microscope. Additionally, there is complementary work that we also can determine the dispersion of the medium. And so that is definitely a pull from unmet needs in production and metrology for transparent parts. That can be glasses, that can be polymers, and whatnot. Then the second use case is closely related, but it's really then for surface inspection. So there can be mirrors, there can be other metal parts, and it's quite flexible here. So what is the situation now? So you can do surface inspection and metrology on the topology of the surface with white light interferometers, with reflectometers and ellipsometers. So very good white light interferometers can go below a nanometer with quite some effort. So again, what we need here is something that at least matches this precision or accuracy, and in the best case gets better and is easier to use. And this common mode interferometer has proven to be very stable. So again, we can here go for a direction where we have better accuracy and precision than with current interferometers and methods, and make that work for high throughput applications. Then an important general topic for metrology and inspection is that some of the workhorses here are non-optical tools, tactile tools, which are just the established method in many industry metrology applications. So there is a push to go towards optical inspection for various reasons here. So one reason why that is, why there is some inertia to go from the tactile to the optical, is really that there is no established traceability. So you can trust both results in the same way. And that's also something where the Q-MIC microscope is, where we are heading for, where we really try to make this traceability then demonstrated. And the third use case is well, quite different topic. It's biosensing or point-of-care devices. So the general roadmap here is that interferometric readouts for such kind of detection have generally an edge on sensitivity. Well, most other schemes either need some kind of label or entirely different schemes which are not optical. So if you really need fast detection, then very often the bottleneck here is really the sensitivity of the readout, and that determines the detection limit. And here again, in early tests with a classical device here, we can already, ICFO has demonstrated quite good sensitivity for certain sepsis markers in that case. And here the direction is very clearly also, the device has intrinsically a very good sensitivity already. Then here it's really important that it is intrinsically, because of the big field of view, you can very easily envision multiplexing with different marker sites to a large degree. And then again, ultimately, we want to see how much we can push the detection limit here just by the increased sensitivity of the device. So here's the general outline where that is going. We are not quite there yet with a quantum microscope. That's very much on the agenda right now. And yes, so, well, the approach is, to say it again, we really need to go for higher sensitivity here for various applications, especially for the biosensing application. That said, for the biosensing application, of course, we also have to go into specificity and other boundary conditions. But the overarching aim of the Q-MIC microscope is to achieve this higher sensitivity that can be enabled by this quantum optical schemes and the novel detectors we are integrating here. Okay, so, well, just to wrap it up, what is our roadmap for actually applying what we are developing here? So I hope it became clear. The classical difference interference contrast microscope in its almost lensless, well, it is lensless with very few optics, realization is already a very good metrology tool. So that the results Luke showed very much demonstrate that. Still, there is a clear pull forward to go to higher sensitivity. There are several avenues to go there. And what makes our platform here really interesting is that there is no intrinsic quantum jump that you really have to completely redesign your interferometric microscope to go from a classical design to the quantum design. Sure, you have to add your nonlinear light sources and the spot arrays and the quantum readout. But from the application side, that is not a disruptive change you have to implement. From the user side, it's mostly a drastic upgrade in the performance. And yes, with that, I'd like to switch to the question and answer part of the webinar we are doing. Oh, I got an umlaut in my name. I saw here. That's nice. Right. So one thing. Let me just check. Wait a moment. Before we address questions from the audience that arose, we have a little poll, which I will start now. Okay, so I hope everybody can see that. So what we would like to know is actually if you could give us a little feedback. So generally, whom we are talking to. So which applications or fields you're actually most interested in. So is it kind of basic research, quantum microscopy generally? Is it metrology, inspection, or are you more inclined to higher health and biosensing applications? And then also for the discussion, well, what we've shown you, would it actually help you right now? Would that be interesting in the direction and the performance that we can offer right now? Or otherwise, well, what would you actually need if you're not happy with what you're showing? So the standard question, what are your unmet needs actually? And well, so feel free. We are all speakers and myself are very happy to address your questions, and I hope the technology works in that case. So I believe at least our audience is at the moment a little shy. So how about our presenters?
Yes, we have a raised hand from Robin. Robin, I'm gonna give you audio. You can talk now.
Hi guys, can you hear me?
Yes.
Yes, great. Thanks a lot for the nice talk. I have one sort of general question about the technology. Like, how do you expect that this technology, so in particular the imaging and the quantum detection, could be improved kind of also beyond the scope of this project? So what are the sort of improvements that we might see in SPAD arrays in the next few years and in quantum detection in the next few years?
Okay, that's, well, the first one is for Francesca, I guess. So
Yes. Okay. Thank you, Robin, for your question. Well, for what SPAD arrays are concerned, I think that the improvements that we can make are on two sides. The first one is in trying to get larger and larger areas. So even more than the 96 by 96 that I presented to you. And in principle, the on-chip detection that I showed can be applied even to bigger arrays because it is based on a tree-like structure that can be repeated several times. And so one way can be the one of enlarging even more the area. Then another improvement that can be done is to trying to have even faster readouts. But for this, I think that even more scaled down technologies are needed. For example, in future, we could go for a 3D stacking technology in which you can have a layer with photodetectors and one layer with the electronics. In this way, we can get a lot of improvement in the electronics. So faster readouts, lower power consumption, but without getting lower performances spuds, because the drawback of improving only the electronics technology is to have worse spuds in terms of detection efficiency and also in terms of fill factor. So if we go to a 3D stacking approach, we can enhance the fill factor because we would have only a layer of photodetectors and down the electronics. And so I think that areas, electronics performances in terms of faster readouts and fill factors are the ways of improving the spud arrays concept.
Thank you.
Francesca.
Yes.
Robin, thanks for the question. I would like to additionally comment something that, well, some implications about this new technology that it's improving year by year will be that once you reach certain time resolution, you will be able to recognize real photon coincidence, multiple photons flying at the same time. What normally happens in real devices that you confuse statistically close photons in time, but they originally didn't belong to the same pair. It's just because statistically they are present in there. So having a really sharp time resolution, you could easily recognize these spurious events from the real.
I agree with you, but the drawback of having very sharp resolution is to have worse the fill factor because you need the area near the spuds, and also increase the power consumption, increase the readout time, all the drawbacks that I showed you with our first array, which is based on high resolution TDCs. So, but of course, having a very sharp resolution can allow you to have only the real coincidences and not the single ones.
It's just a matter of time.
It's a matter of time. It is a matter of how many real pairs you have and instead how many single photons you have. So it is also a matter of how is the source.
Obviously, yeah, you can, by improving the source quality, reducing losses, you can preserve as much as possible the original photon pairs or photons.
Yes, exactly.
Okay, so I stopped the poll so far. So thanks for participating. So well, on the good side, everybody who participated said that would be helpful what we are doing. So we are pleased to hear that. Now from the application side, it's pretty much mixed. So we got a couple of answers for each part: quantum microscopy, metrology, and health and biosensing. And so in the chat from Johannes Johansson, there are two questions. A general question about the interferometric imaging technique. So he asks, are you able to differentiate index of refraction and object thickness? Yes, that's a very good question. So maybe Luke, can you comment on that?
Yeah, thank you for your question. If this is the only one I will answer, otherwise I can give you the voice later. So we are not directly able to differentiate between refractive index and the thickness, but since we can use many different kind of wavelengths and also reflection and transmission mode, we can then start to distinguish the two and also make estimations about that. So you can imagine that if we have different wavelengths, for example, then we can figure out the dispersion curve. And also for transmission and reflection measurements, there will be a difference in the two. I hope this answers your question. I will unmute you now if you have further questions.
Yeah, thank you. What was interesting. And I also have another question, actually. If,
Sure.
Does the material need to be completely transparent, or can there be some scattering in the material and you still get something useful out of it? So
to your first part, the material does not have to be completely transparent. It can be semi-transparent, reflective, kind of nearly all kind of ways there. If it is scattering, we will mainly measure the unscattered light. So we will, because it's kind of acting as a filter for the direct reflected or transmitted light. So that's why we will kind of filter out any scattered light, which can be useful. Does this answer your question?
I think so. Thank you.
Okay, great.
Okay, there's another question in the chat from Yunyan Ma. I think it's directed to Francesca. So how did you do it? Well, I just read it. I'm wondering about the design of the circuit on the chip. So how did you pick up each small circuit module? So it's about the actual process of the SPAT assembling. So
yeah. I mean, the question is also, does any university or company help you generate your this wonderful chip? Okay, so thank you. And we, our SPAD lab group, our group in Politecnico di Milano designed completely this circuit, this imager based on that detection concept. So it is our design, and well, I mean, I don't know what you really want to know. I can recap that it is a circuit that is an imager that can can understand if a coincidence has happened, and which tells you the addresses of coincidences only if the coincidence happened, and only the addresses of the pixels involved. Of course, it is dirty up by singles, as Alvaro was before asking me. But of course, we do not need to read all the arrays, and so we are skipping much time, and we get a very fast readout of only useful data. That's the main advantage of this detection concept.
Mm-hmm. Okay. Thank you.
Okay.
There is another question. Sorry,
yeah,
there's another question in the chat from Alexander Demuth. That's directed to me. Does ZEISS have already comparable image devices? The answer is yes, we do. In the sense that we do have optical inspection devices, we do have interferometers that have already very high sensitivity. I mentioned it's going to angstroms already with conventional technology. Then there are confocal devices for surface inspection. Now, having said that, what we are aiming for here is really an interferometric inspection tool that is as sensitive as at least state-of-the-art interferometers, and additionally allows for the use cases transparent optics and surface inspection, also for fast throughput. And in that sense, standard white light interferometers, or even the advanced ones, are not very well suited for that particular unmet need. And additionally, already and especially in the classical version that Luke's showed, the DIC is a common mode interferometer. So the need for regular calibration should intrinsically be much lower. So you get a very precise tool, which is, well, it's wide field, and it has this intrinsic high sensitivity. So, I mean, there is a trade-off, of course. The sensitivity in that configuration comes to a large degree from the lack of imaging optics, so to say. So you have a trade-off in the lateral resolution, but there are definitely tasks, as the three outlined here, where a lateral resolution that is in the range of micrometer is tolerable because you don't need a better resolution there. What counts is there the sensitivity. And so I hope that answered the question. Otherwise, at the moment, that also can unmute you if you want.
No, thanks. Thanks for answering the question. It's all fine. So I posted another question, so maybe I could just ask it.
Here we are.
It applies to everybody. Could you comment on similarities with and differences to the Super Twin European project, because it seems quite similar to me.
Now help me quickly. Is the name as telling as it sounds? Because I don't know it in depth. Is it with optical twin beams as detection?
No, it's also using this type of Noon states to have some super resolution.
Well, in that sense, yes. If it's using Noon states, it's probably from the quantum optics side similar. I can't comment on the details. So I mean to add on to what Alvaro said. So what we are going here for is really a more general scheme. So I think with Noon states alone, if you go into somewhat lossy samples, that alone is not a winning proposition, I think, because the Noon states alone are just too fragile. Having said that, if you have a light source where you have, let's say, more correlated photons than in just a laser light or a thermal light, and you have, on the other end, a detection scheme that can really get the information out of those correlations, that's a useful add-on in any case. So the idea would basically that I keep all the information I can extract from standard detection, and then additionally, I also extract extra information from the correlated photons. But I have to do both. So that's why it's here so important to have really high-performing SPADs with the low dead time and fast readout logic at the back end. So I'll have a closer look into SuperTwin. So if there are synergies, we should certainly look into that. But at the moment, that's my answer here. Okay, so I don't see any more questions in the chat. So as we have a sharp hour for that, I will can discuss a little bit. I will just make the general comment. This webinar, as we do it right now, will be available on the Q-MIC website, and there also you will find all our contact information. So at least the emails, I suppose. So if you have questions you didn't ask right now, or you have some later or so, don't hesitate to contact us. I mean, we just had now a little cross section about the activity, what the consortium is doing. Feel free to go for that. Now I think that there's another raised hand in the audience.
Johannes here again.
Yes.
I wrote a question in the chat for Francesca here, actually, about
okay, yes, about
the dead time of the detector.
You mean the one I mentioned of 330 nanoseconds?
Yeah, exactly.
Okay. Okay. That is the readout time of our SPAD array, and in this case cannot be shortened. It is already a very short time for a 96 by 96 detector, because usually these dimension SPADs require tens of microseconds to be read. A way to shorten it would be to use a more scaled down technology, but that would worsen the detector itself performances.
So it wasn't actually it was the readout time, not the...
Yeah, the readout time.
So you could have a multiple photon detections in this time interval on each pixel.
I call it dead time because that is the readout time, and in that time all the detectors are like dead. We cannot see anything in that 330 nanoseconds.
Thank you.
Okay.
Okay, the hour is over. So as said, you're very welcome to post us more questions and whatever interests you about our microscope and the parts of it.
Ulrich,
yes,
I would like to comment something that.
Sure.
Respect to the Super LIM, maybe one of the main difference between that technique and that project and ours, that their aim is to increase the transversal resolution that they are measuring. Okay, that's not our focus. We are trying to increase the phase resolution, so the thickness resolution that we are measuring.
Okay.
Devices are still single photon SPAD arrays, but with different architecture because of what we have explained. I don't have details about how their platforms work exactly, but this is the main difference.
Thanks for directly clarifying that. Okay. All right. So we are out of time. So as said, if any more interest is there, we are open for questions through all channels. Otherwise, yes, I have to make a wrap up. So thanks everybody for the questions and the interaction. Thanks my fellow speakers. And I hope you have still more interesting sessions within Future Tech Week. And with that, thanks and goodbye.